Got it. By golly, I got it, and we've got it, and there's four of us, and it's Talking Heads time again. Santa Barbara, California's own Telescope and Astrophysics Club gathering again on the screen as we have 124 times before, ladies and gentlemen. It's the SBAU, stands for Santa Barbara Astronomical Unit, and the SBAU Astro Hour. Besides a 20-second delay, we're mostly live on YouTube every Monday morning this time. I'm Ron Herron, your host. I'll introduce you to the other guys. We have a blog podcast where we talk about everything cosmic, and by golly, we've done a lot of stuff. You can go online, sbau.org, learn all about us. Come to one of our star parties on the second Saturday of the month. We just had an awesome one, and I greeted myself personally, a lot of you, and we'll get our outreach coordinator to give us an update here in a minute. We're going to learn about cosmic dust this hour. Here's what's going on. Oh, let me introduce the gang, and then let me tell you quickly, get everybody salivating about cosmic dust. The new comet arrived. In fact, we talk a couple of comets, 237P Linear, whatever that is, twilight, and crepuscular rays. Those are two separate items, Mr. President. Separated in your talking points. Maybe we could put them together since they're very, very similar. Japan's orbiter around Venus has been up there for a few years. We'll give you an update, what it's finding. We're going to look at the double cluster in Perseus, this show, and all about neutrinos. I have wondered about these little guys. They're passing through our bodies right now, right through the Earth. And everything from cosmic dust to neutrinos. Going to be a heck of an hour. Let's meet the presidents after all these years in glorious white, both beard and top. Jerry Wilson, married to that lovely Pat, who said the nicest thing to me on Friday night at our big meeting, and thank her for that. Hope to have fun talking to these people. We just booked Bob Berman, I guess a columnist for Astronomy Magazine, for October, working on September, and then next month on August 4th, it'll be your old friend, Dr. Peter Love, talking about the Webb telescope. Here's Chuck McPartland, our outreach coordinator guy. I don't know how he does it, but he sets that machine up how many times a week? Or 200 times a year, right? You go out
in the neighborhood.
Well, that would be four times a week, wouldn't it? Right? That would be 4 times a week average.
Yeah.
Bacara, we're going, well, I'll get a report from you here in a minute. Yeah. And one of our stalwart, you know what, I don't have, I'm doing this all from the top of my head. I normally have a sheet here, but I'll just tell you, Bruce Murdoch is an incredible member of the club. He probably likes our club as much, if not more, than he likes the club that he's president of, the Santa Barbara Theater Organ Society. Bruce, thanks for coming on board. You there?
Yes, I'm here. Hello.
Can I introduce you to somebody? Come over here. This is my granddaughter who's visiting from Pittsburgh, and she is a straight A student. She's 15 years old, has an amazing amount of storytelling in her. She wrote a story that's just awesome. Come in here close to Grandpa. And she's gotten a scholarship, and I invited her to take part. Is that okay with you guys?
And what's her name?
Oh, I call her geocentric. Her name is Giovanna.
Giovanna.
She's geocentric to me.
Welcome, Giovanna.
Hi.
Hello.
Good Italian name, huh?
She just has a taste of you like science, right?
Mm-hmm.
But as far as astronomy, it hasn't taken hold yet, has it?
I don't really learn much about it.
Well, you're gonna. Not with this hour. Anything you want to interject? Well, once we get going to talk about these things, we start with a little levity. So you just position yourself right there, Gio, and watch the talking heads get us all going here. Best thing I found on the internet last year, I think.
I like this.
What is this? Rocket scientists built a replica, the Gary Larson rocket, the stunted one that actually flew quite well. Is that true? That sucker got off the ground?
I have no idea. I just take their word for it.
As long as the center of force out of the rocket engine is in line with the center of gravity of the rocket, it really doesn't quite matter what shape it is.
They did change the fin structure. This fin is part way up, and these are all down.
Oh,
so they did give to aerodynamics.
Fins have all but disappeared from modern day rockets, haven't they? I guess they use jets instead to keep it.
They have gimbaled nozzles. Plus, if you look at the Falcon 9 rockets, they actually have little fins that are in the form of paddles that look like fly swatters. They've got holes in them that come out for aerodynamic control.
Well, speaking of aerodynamics, I've always thought it should be as streamlined as possible, clear to the top, to the point, and yet all the SpaceX things, Elon Musk's have a bulbous head on the top. Have you noticed?
Well,
Well,
that's
they-
to fit the cargo in.
Yeah,
I suppose, but
that's when the cargo is bigger than the rocket.
okay, that's the reason for that.
Yeah.
It all
Okay.
depends where the force is put on it and its speed, because the drag goes as the square of the speed. And,
Oh,
if you get, once you get above the atmosphere, once you get up, 30, 40, 50 miles, or even just
Doesn't
30
matter.
miles, 20, you lose the aerodynamic drag drops precipitously. So it really doesn't matter what the shape of the rocket is.
Yeah.
right. Here are the jet fighters of the future. Plug it in.
Yeah. You got to
I'm
get better batteries.
And your Tesla drivers are going to want one of those for the road. What are we talking about here? Some aliens or are these
Yeah.
humans? These are aliens. Well, I've given the creature sustenance, talking about a cat. The other one says, I had already done this. And he says to him, well, wait a minute, their receptacle was empty. Okay, says the other guy, the creature emptied it. No, their request seemed desperate. It was deception, character. There it is again. Now the creature mocks us. What's it doing? Meowing? Am I missing something on this?
Yep. No, just a cat begging for food and attention. And when you pay attention to it, it'll walk away and say, I don't care.
That's right. Cats are in control. I know. Here we go. The metric people. Yep. The following, no cussing. The following 4-letter words are forbidden here. Inch, mile, pint, foot, yard, acre. There was another one I came up with and I can't remember. And we never swear the big F, as in Fahrenheit. Use centigrade. Please keep it clean and metric. Okay, and then back in the old days, way in the old days, we have dinosaurs assembling, and one of them says, whoa, the word of the day is extinction, just like in today's horoscope. That was the beginning of the end of the serendipity age, 65 million years ago. And we're back to that again. There's some good stuff. What happened to, maybe you have it all, dinosaurs, orbit, or the third stage of Apollo 12. That was a video that we all.
Oh, that was a video I just sent for you guys. We're not going to discuss that.
Okay, it was fascinating. Well, just to say there's a new, a moon that's man-made, or is it orbiting in its own orbit? It's the third stage of a Apollo 12 rocket blast to the moon way back, Apollo, right?
Quite a while ago, yeah.
Okay, I watched it. It was
Apollo 12.
How are we doing so far?
Good.
Jerry, when you add a link in your emails, and like it's YouTube and it's YOU dot something, or they fractured the name. I won't open that because I think somebody's done something weird.
Oh,
Really?
And so the
Goes right to your spam. Huh?
I had the other night I opened to something or other, and all of a sudden this thing comes up, your computer is infected, blah blah, you got to call this number, and I couldn't get out of it, so I just turned the computer off and on again and ran my virus check. I didn't find anything.
Yeah, somebody sent me truthfinder.com and I looked up somebody I used to know, and the damn thing just keeps sending stuff to my screen. It won't leave me alone. Can you enlarge that just one more time, Jerry? And we'll talk about cosmic dust, also known as never believe in atoms. They make up everything.
yeah.
Okay, that's inside of stars or plasma. This is a cosmic dust. We're going to get the definition that's different from our vacuum cleaner contents.
No, pretty much the same.
Okay, these are things that might be in the plasma or in the dust. The dust is not plasma.
Well, we'll start. This is a sequence from top to bottom.
Oh, it's sequence.
So
Okay.
inside of stars, it's all plasma. That is,
Right.
it's torn apart atoms and fundamental particles. And that plasma consists of nuclei, electrons, muons, and other elementary particles.
Okay.
So in the fusion process, when the temperature gets real high because of compression due to gravity of the mass of material that makes up the star, then nuclei are formed by fusion, and these nuclei consist of both protons and neutrons. And of course, a neutron is a proton, electron, and a muon.
Squeezed together somehow.
Yeah, squeezed together somehow.
Wow.
And then heat, the somehow is heat. When heat means speed in terms of this. So when two things hit each other with enough speed, then they break through their repulsion and they collide and they stick. And that's how you build up atomic nuclei that are more than just proton of hydrogen. You know, you can build up, and then when hydrogen stops fusing, gravity compresses a little more and the temperature goes up and you start making hydrogen into helium and et cetera, on up to iron.
Right.
So these nuclei are kept in an excited state. Electrons stick to protons to make neutrons, but electrons do not stick to nuclei to form atoms. When individual particles collide, they bounce off each other because the temperature is so high. They do not stick together unless they are fusing. So when this plasma is expelled from the star, its components are suddenly in a lower energy environment. They're outside the star. And so their speed slows way down and they can now start interacting with each other. And the plasma, there's many ways that the plasma is expelled from the star. It's expelled by a solar wind or stellar wind, cosmic or
Coronal mass ejection.
thank you. Formation of a planetary nebula, nova, or supernova. When the plasma components that were separate in the star bump into each other, they now stick together. And when they stick together, atoms are formed, nuclei plus electrons. So the electrons now start filling in the nuclear shells that the nucleus provides. Atoms combine to make molecules. And this all happens very quickly in many cases. It doesn't, happen under a mountain. It's very dense and it's very a lot of energy around, but it's sometimes very quick. Molecules then, what's that?
Microseconds?
I don't know the exact same scale, but it's a variation of scales. How long it takes for a supernova to blow up, it's going to be a time varying pressure inside. But and the times run from a few microseconds to probably weeks. Atoms then combine to make molecules when they bump into each other. Molecules combine to make compounds and minerals. And these in turn combine to make grains or dust grains. And that's where dust comes from.
Okay, so they don't have gazillions of atoms. They're not like remnants of something larger.
No, dust depends on your gazillions. When they make grains and dust grains, they have at least on the order of 10 to the 23rd atoms in them. That is, they become macroscopic. They're no longer microscopic.
Okay, but molecules that become compounds, for example, salt is the molecule of what is it? Sodium and chloride.
Sodium and chlorine.
And that's all that there is in salt, unless it gets other things, right?
No, that's all. That's salt. If they get other things, then it's other things.
Well, I'm thinking
But
about
one of the most common things that is made in in these explosions is water. That's a compound, H2O.
Oh, yeah.
Tons of it.
That's our favorite compound.
The water is the universe is full of water. Now, this is a picture you didn't get, but this is a recent James Webb Telescope picture of a supernova 2004 ET and 2017 EAW. And these colors around here, the hexagonal pattern, of course, is the structure of the James Webb Telescope. But the colors around here are dust from a supernova remnant. Supernovas are one of the prolific producers of dust. So
we're talking about what's called population 2, the second generation heading for us that gave us this.
No, Ron. Population 2 stars will incorporate this stuff into their structure.
Yeah.
Okay, well, we're made up of the higher elements, obviously, that weren't in population 3 at the beginning.
No, we're in population 1.
I understand that.
It's backwards.
Yeah.
It is backwards. But now this isn't that nearby galaxy supernova.
No, this is not the M101 supernova.
Those numbers
These
you
are
gave
supernovas that happened 20 years ago on the left and 6 years ago on the right. So they're pretty much over. Now you just see the crap coming out. It's going to form it's dust, and it's going to form a nebula, possibly.
Okay.
So,
Well, our zodiacal light is the dust within the plane of the solar system.
right. Now that dust is also, once you make it from a source like this, once you make a solar system, collision is the name of the game in producing that disk and producing planets and asteroids out of it. And they run into each other all the time. It's how we got our moon. And a lot of this components of protoplanets is splattered off into space. Asteroids collide with each other and produce a lot of dust, pebbles, and crap.
Yeah, but
By the way, crap is a technical chemical term.
what's a
Crap. It's a
crap.
technical term in chemistry.
But something we've never seen, as far as I know, is two big bodies colliding, like you
No,
said,
we've seen asteroids collide.
Really? Where you
Yep.
actually see them fragment up and
Yes.
burst apart, and
They
maybe-
grow a tail, basically.
I've never seen one. Have you, Bruce?
No, I haven't either, but that doesn't, I don't, there's a lot of asteroids.
No,
In 94, we saw a comet collide with Jupiter.
Oh, yes, Schumacher-Levy.
yeah, and that gave us big black spots on the planet's surface, but it's not the same.
Now there, all the dust was probably retained by Jupiter.
We actually couldn't see the collision because it was on the backside of Jupiter. You
Yeah,
could see
we
the
weren't.
holes that punctured in the gas layer as the planet rotated.
And somehow the comet, when it was coming in, decided to divide up and become a string of smaller pieces. didn't it?
That was tidal forces from the gravity.
Jupiter tore it apart. It came within the Roche limit for that.
Yeah.
I just try to imagine in my fantasies what it would be like if another moon or a planet came to us. Would we suddenly want to fall up to that before it crashed? Would we
Depends
die?
how massive it was and how close it was.
Ah, okay. Gotcha. Fascinating. Which galaxy are these pictures in? Or that's the same one?
That was not identified here. I think it's our galaxy. Well, no, it's a supernova.
Yeah.
I don't know.
Okay, but
Maybe.
the
That
recent
wasn't the point of this.
a
So,
Japanese guy on his telescope, an amateur, discovered the recent one, right? That's still blowing apart in a galaxy.
Right,
not
in
far-
M101, yes.
yeah.
Okay, we don't have a picture of that. What is this?
This is Comet Atlas.
Ah, we have a comet named Atlas.
Yes. This is a photograph, and it was a time exposure photograph. And you notice the stars are not smeared, but the comet is. So this is the head of the comet, and it moved during its exposure. I don't know if it moved this way or that way, but it moved.
Like it moves sideways.
Yeah, it moved this way along
Yeah,
this
yeah.
axis.
Right.
And it's interesting because it's near this galaxy called Hoag's object, which is one of the first ring galaxies.
Well, found by a guy named Hoag, I assume.
Yes, Arthur
19
Hoag.
And it's in Serpens Caput or Caput.
Yeah.
Serpens Caput, the head of the snake.
Head of the snake.
Mhm.
Ring, an unusual ring galaxy.
So this is the constellation of Serpens Caput. There's also another Serpens, the tail of the snake, or this is the tail.
No, that's the
Caput.
head.
The head,
Caput is
okay.
head, Cauda is tail.
Cauda, yeah. Okay.
Okay.
It always sounds like an Italian food, cauda.
Yeah.
Okay.
So this is the boundaries of the constellation. And in there, this cursor marks Hoag's object. It's up in here. A very familiar thing, easier to spot, is Hercules with M13.
Oh, yeah. Okay.
But the comet,
Arcturus in the upper right.
the comet is C2019, T4. It's also called Atlas, but it was found, what, 4 years ago? First seen?
If it's
Yeah,
2019, yes.
Yeah.
Okay. Well, we got to see that. Is
So this was photographed by Ira Bell from the Sierra Remote Observatory. Now, what that is a plot of land in the Sierra Nevada mountains that where the land is rented out to individual amateurs and institutions that have a telescope there that's run remotely, and the staff at the Sierra Remote Observatory, they maintain the telescopes, but the owner operates it. So it's a small clustering of telescopes that are set up there. It costs quite a bit of money. I've looked at that. I decided to build my own backyard observatory.
By the way, you did a nice job on that.
I was waiting for this. This is a galaxy we're looking at.
Yeah, this is Hoag's object.
Well, it's a galaxy, isn't it?
Yeah,
Yes.
it's a galaxy. This is the
Okay.
core, the nucleus, and this is the
You don't see
Yes.
that very often.
star
in galaxies.
formation ring.
Normally a spiral. Why isn't it spiraling out?
Well, we had a session on that about a year ago, that these are the result of, in general, they're believed to be the result of a galaxy collision where another galaxy hit a spiral galaxy right in the center, just like a bullseye. And it splattered this ring of star formation out radially from it. And that's where you get this structure. And interestingly enough, you can see another Hoag type object in the background of this Hoag's object here. There's another
Wow.
ring galaxy back there.
Jeez.
Yeah, really cool.
Oh, okay.
That looks like a big star in the middle, but that's more or less the center of the galaxy.
Yeah, that's a lot of stars.
Black hole, and in between is nothing, or just scattered smaller.
No, it's stars too, but it's not as near active region producing as much light as the ring around here. So a lot of the stars in here were blown out here.
Is my granddaughter taken over by any of this? She's watching. I predict she's going to be a great astronomer someday. You
Okay.
will. All right, here we go.
Now, this is the other comet we're going to look at today, linear.
237P, named after Linear, L-I-N-E, or Linear.
Linear is an acronym for the instrument that found it. It's an automatic comet search routine.
It's
Okay.
Lincoln Laboratories Near Earth Asteroid Search.
Have
Yes.
any of you ever focused on it recently?
No,
Oh,
You can't, or you just don't get around to it?
good.
Hmm.
I mean, it's fairly dim.
Oh, is it? Is it coming our way?
Well, it's periodic, so it may be, or it may be on
Yeah.
its way out.
Okay, it's not a regular like Halley's.
Yes, that's what the P means. It's periodic.
Oh,
Yeah.
what's the 237 mean?
That's the 237th periodic asteroid for which an orbit has been determined.
Not asteroid, but comet. They're kind of
Comet.
similar.
yeah, comet, yeah.
Okay, fascinating. Okay,
And this is in the constellation of Aquila,
okay,
the eagle.
all right.
This
Rising.
is is an ephemeris. Let's see if I have the picture. This is the
Oh,
trail.
that's horrible.
See, I either have to endure Chuck's comment or I have to transfer this curve to a more reasonable planetarium. So sometimes I do one, sometimes the other. Two nice things over here, a globular cluster and a galaxy. Or is this an open cluster?
That's I think that's a planetary nebula symbol.
Yes, that's right. It is. I've got a thing on that coming up. Yeah. How quickly I forget. So this is July, what are we, 10th right there. So that is there. The ephemeris, it gives the right ascension and declination as a function of time. So this is a tabular statement of that, but it shows the magnitude and it's keeping about constant at about 13, between 13 and 14th magnitude. So it's moving away from us because it's getting slightly dimmer.
Hmm.
And a 13th magnitude is the limiting magnitude for a 6-inch amateur scope. So you won't see it unless you're even if you're at a super dark sky. You need at least an 8-inch or a 10-inch scope to be able to pick this out, and then it would be faint.
Or a smaller scope with a camera.
Yes.
Are
Yes.
there ever appearances of comets that you can see during the daytime?
Yes.
Really?
Achilles.
Yeah. The several religious sects killed themselves, and everybody thinks the world's coming to an end.
Okay, that wasn't Halley's, but it was one.
Oh, Halley's what? It was in 1910 or thereabouts. Could be seen during the daytime.
Yeah.
Every 70 something years. Okay, we're going.
Now, for Halley's Comet, it came by in what was it? There was in 76 or 86.
85.
85, okay. And then it came by around the late 1800s, 1890 something.
1910.
1910.
1910? Okay. Well, there was a big campaign of fear in the newspapers. You know how the press likes to be sensational.
Yeah.
And
Well,
so
so
someone
newspapers.
pointed out the Earth was going to fly through the tail of Halley's Comet. And spectroscopically, they identified several problem molecules like cyanide in the tail of the comet. And so people started selling gas masks and writing horrible stories of what was going to happen to the population when we passed through the comet's tail.
Well, do we still pass through its tail? Is it one of the meteorite events?
Well, you pass through its orbital path, yeah. So
Yeah.
you could think of that as a little bit like the tail,
Yeah.
but
I got you.
But it's all just
Cyanide they had
sensationalism.
was probably only a few molecules per square meter or cubic meter, right? Very, very sparse.
Very
yeah,
sparse.
for Hale-Bopp, which had a huge tail, going 16 million miles or something like that. The estimate was if you took all the particles in the tail, you could fill a suitcase.
But back in Halley's time, the man who found it, they'd have to see the comet to report on it and know what's out there. These comets we're talking about, we'd never see them with our naked eye.
Right.
Yeah.
Galileo didn't focus on comets, did he? I don't think he did.
No.
Did he? He
No,
was.
Messier did.
Do your telescopes track them? Can they track them just like it tracks the Earth?
And
Yes.
It can. It's a separate tracking thing, though, isn't
Yep.
it?
you'd need to have it driven by a microprocessor that has the orbital elements of the comet.
Mhm.
Okay.
Or you can just
Then-
have a star tracker that tracks the bright object, the centroid of the object. And in that case, if you took a picture, the comet would be a point, but all the stars in the field would be lines.
Yeah, you can't win.
Yeah.
And we've sent some
Do a double
probes.
exposure.
We sent some probes out to a comet or two and got some dust, didn't we? Back.
Yes.
Yeah.
Did we learn anything? Are we not going to do that anymore?
No, we'll probably do that again. They're talking
Yeah.
about, especially if we get another interstellar comet.
Yeah.
But I mean, it's different dust. We're talking about cosmic dust. That's definitely dust of some sort behind a comet.
And water vapor too. They're looking at the isotopes of hydrogen and oxygen in the water to try to determine if the water on the Earth came mostly from comets or mostly from meteorites. And it seems to be a mix. So.
And water in the comet, in the rock, is what gives it the tail. The sunshine from the sun hits it, and that doesn't
The
happen.
ice turns into vapor. Yeah.
It's
Okay,
also
gotcha.
CO2 ice.
Yeah.
Oh,
And carbon
Yeah.
monoxide ice, all kinds of ices.
So in the same region as the comet, which is over here near Altair. Oops, yeah, there. Over there is NGC 6790. This is the planetary nebula that
Okay.
had that symbol. Whoops. 6790 here. And that is located along this line of the constellation. And this is what it looks like in the Hubble. This is a very small, very young planetary nebula. And you can see how poor the photograph is. It's not terribly sharp. It's because it's a very small thing. So it would be very difficult to tell this from a star, a faint fuzzy. But it's a good object if you want to test your equipment and your eyesight.
And you could blink an O3 filter and probably see it was different from stars if you wanted.
Yes, that makes these planetary nebulas stand out tremendously in a visual scope.
so this wouldn't have been taken by the Webb then, would it?
No, this is not the Webb.
Okay. And Webb is a busy scope these days. There's so much to look at. Amazing stuff. Let's see.
Okay.
We had Damarung with the different versions of Twilight. Did you want to go there and talk crepuscular rays? Oh, yeah. Here
Just
we go.
real simple. The sometimes you see these terms crop up. For us, we like a dark night, but these things have very specific meanings. So civil twilight ends when the sun is 6 degrees below the horizon. Nautical twilight ends when the sun is 12 degrees below the horizon. And 18 degrees, which is getting to really dark, is what we astronomers think that the night has begun. So that's the dim light. Now, during these twilight periods and during these dawn periods, which is also a twilight, looking at planets, it lowers the contrast, which in the case of Venus is an eye relief, and you actually see a better image of the planet during these twilight times. And if you can catch it during the daytime, it's much easier to view in the daytime. And it's not difficult to get Venus during the daytime. You set your scope up to look at it at nighttime, and that defines the declination it's on. And so during the next day, you then move along that declination until you pass, and you move in right ascension until you pass Venus, and then you see it.
Well, I got to tell you, gentlemen, I like to take my walks alone on the right side at sunrise during twilight and do my work in the yard on the left side with sunset.
Yeah.
Because
Dämmerung is German for twilight.
is that what it is?
Yeah.
Dämmerung. Okay.
Gota Dämmerung means twilight of the gods. A Wagner piece.
There was a movie series called Twilight. It was about vampires, wasn't it?
Yeah, yeah.
Did you read that?
It was also the Twilight Zone.
That's true too.
Rod Serling.
Now
You know what
this is a very nice picture of Venus that was the apod for, I didn't put down the time.
the Japan launched the
For July
Akatsuki.
3rd. It was taken by the Akatsuki satellite Venus probe,
Right.
spacecraft, on July, and it was presented on the astronomy photo of the day on July 3rd of this year.
So was it back 2015 they launched, and it's been orbiting ever since. Took 5 years to get there though, didn't it?
Yes, so it's taken a while to get down the energy well to Venus without hitting the sun and without getting flung out of the system. But the thing is, in near ultraviolet, this is a gibbous phase from the point of view of the satellite. And you can see structure on the surface in through the atmosphere.
Really?
Yeah. Was it ultraviolet or infrared?
It was ultraviolet.
Okay.
Ultraviolet. Okay. The three questions, according to your talking points, Jerry: volcanoes, are they still active? I thought they were. Lightning in the Venus atmosphere, and the wind
All the
speed.
time.
Why is the
Yeah,
wind?
there's all those are there. The Akatsuki.
Akatsuki.
I didn't try and learn Japanese.
Akatsuki.
The
Pronounce every syllable.
is studying those things in detail. That's the purpose of it. It has wind speeds that are faster than the planet's rotation. Of course, the planet rotates very, very slowly.
But they're not going to think about landing on Venus.
No, they're thinking about it. They're thinking more about putting blimp-like probes in the atmosphere, because apparently above the dense layers of acidic air, there's CO2 atmosphere, and it's not so hot and it's not so caustic.
And they're also talking about making rovers that aren't quite so dependent on microelectronics that really get messed up by the heat.
Yeah.
So almost
use
like a
analog.
wind-up toy.
Have to make analog computers like they used in the gun directors in Second World War.
But I got to tell you, there's something similar if you landed a craft with people in it to that submersible that wasted away and above the Titanic. It'd be the same effect, wouldn't it?
Atmospheric pressure at the surface of Venus is like being 3,000 feet underwater on the Earth.
By a strange coincidence.
Yeah.
Okay.
So this is in the category of a very pretty picture, and it has information in it too. But right now, this is what Venus looks like in the sky this evening.
Crescent.
It's very bright. It's a crescent. This was taken a few days ago.
And if you watch over the coming days, the crescent will be getting thinner but taller.
Yes, it'll be getting bigger. Right now, Venus is at its maximum, roughly at its maximum brightness. And as the crescent gets thinner, it will get to the point of getting losing a lot of its brightness. If it goes sufficiently far from the sun, pictures have been taken that show an entire ring of light around Venus where the sun shines through the atmosphere. It's a very dramatic picture, very hard to get.
What do you suppose the Japanese are going to do with the Akatsuki? Just leave it there forever? Does it?
Well, it's got a mission. I don't know the mission in detail, but it will probably perform its mission. And then if they decide to keep funding it and they find interesting stuff, that they'll keep funding the mission.
Otherwise, they're liable to just drop it into the atmosphere and burn it up.
Yeah, the standard agreement is that we don't leave things orbiting other things.
Well, Russia's got some probes or landing craft on Venus, don't they? Several.
Yes, it's sitting there.
Yeah, they only lasted about an hour before they cooked themselves.
I wonder what they look like now. You suppose they melt? Or
maybe they look like the Titanic on the bottom of the ocean, with all these dribbles
With the
of iron.
sulfuric acid, yeah.
Your notes, Jerry, said that
joints in Venus's and in Russia's Venus probe have melted.
yeah. Well, according to your talking points, there's a jet stream it's like our Earth jet stream on Venus they've discovered. And I guess that's what that picture right there.
Yeah, all these cloud patterns, they're all shaped like this. The jet stream goes equatorially around this way. It may reflow on the ends. I don't know about that. But if they want to study, it's a strange wind pattern.
Whenever we see a picture like this, we can assume that the top of the ball is the north, the bottom is the south, and
no, you can't assume that.
We could be looking at it upside down, huh?
Well,
Any
upside
orientation.
down doesn't have much of a meaning.
Yeah.
But most bodies in the solar system have an equator, don't they? All the moons, everything
Yes.
has an equatorial region. I wonder where it is in this picture.
Oh, it's along this line right there.
Oh,
That's where the jet stream goes.
So these are the poles, but which one is north and which one is south, if it's any meaning, I don't know.
I'm just trying to get an idea of what the Earth's going to look like someday. Hopefully not during my life.
If
Wow.
we don't
We're
start,
working on it.
if we don't, yeah, go ahead.
No, just
If
Go
we
ahead.
don't start filling our atmosphere with CO2, this is the end game for the Earth.
Yeah, I know. How about crepuscular rays? Okay, there they are, I assume. What the heck are
Yep.
what is crepuscular? I've never heard that word in my life.
crepuscular means between night and day. So you have like creatures in the desert are crepuscular. It's too hot during the day, so they're active at dawn and dusk.
All right, Bruce, have you ever heard that word before?
I have, and I have pictures of them actually more in the day. When I was driving across Idaho at one time, there were some clouds, and the rays of the sun were coming through the clouds, much like you see in this picture here, upside down though.
Yeah.
But this is not happening during twilight, though. The sun hasn't set.
This is
But-
here.
The sun
Oh, it
is
is?
bright. I think that's the sun right there, or else it's a very bright cloud.
Just about to set.
Yeah.
Does it require clouds to give us crepuscular rays?
Yeah, it requires something to be shined through, and there's enough haze in the atmosphere that you can see the rays of light scatter. If the atmosphere were completely clear, you wouldn't see the rays. It has to
Okay.
scatter off something. Now,
And
when
then you
you see
ahead.
this crepuscular rays, and in the opposite, if you turn your head 180 degrees, and the conditions are right, you can see anti-crepuscular rays because they come together again on the opposite part of the sky.
Oh, really? Okay.
That's a very rare picture, but I have seen it.
okay, is the bright green flash a crepuscular ray?
No,
No,
that has nothing to do with it.
That has nothing to do with it.
That's the atmosphere acting like a prism, and it scans the different colors of the rainbow past your eye, and your eye is most sensitive to green, so that's the one you pick out and remember.
But there's a whole range of stuff that people have noted the sun does when it sets. They can see 3 versions.
Yeah, oh yeah, there's a lot of atmospheric refraction going on.
Wow. Why we love this hour, don't we? So the double cluster Perseus, is that where we're going next?
Yeah, real quick.
A double cluster.
2 clusters right close together.
this is
Okay.
real early morning.
Yes. This is the Cassiopeia up here. And
Okay.
this is Perseus down here, and right between the two constellations, if it's a dark sky, you can see this visually. You can see the double cluster with the naked eye right there. And what it looks like, see, there's two clusters right close together. This one down here has more red giants in it than this one does. And if you look at them during right toward the end of astronomical twilight or during astronomical twilight, for some reason it makes the reddish stars stand out. It's a very vivid visual.
Especially that one kind of on a line between them there, closer to the bottom one. That one shows up really bright red.
Yeah. Yeah, very colorful.
Is the big W of Cassiopeia enclosed in this picture?
No, no.
This one, this is
very
very
small.
tight on this
Okay, got it. Okay.
this region right here. That
So-
whole picture is right under this hand. Here's the W up here of
Okay.
Cassiopeia. Actually, it ends at Rukba.
So we're talking about two big clusters of stars.
Yeah.
Globular clusters that
No.
orbit each other,
No, they're not globulars. They're open clusters.
open clusters, meaning, what does that mean?
Young stars.
They're not orbiting each other or a common,
No,
They
they're
are,
not.
yeah. They're bound, but they're not a huge cluster of old stars, which is what a globular is.
And they're slowly drifting apart because each one of them has its own idea of an orbit around the galaxy.
might it have been in a orbiting galaxy that our galaxy captured?
No,
One of those?
no, these are young
Our
stars.
Oh, they're young local stars, okay. Double cluster, interesting. It's gonna take a while for it to happen though, isn't it? Those,
Yeah,
you say they're going apart, we're not gonna see it happen in
No.
our lifetime.
no. But our sun came from an open cluster
Did it
and
really?
it drifted apart.
How do we know that?
This is a stage in the
Okay.
development of stars. This
Stars
used
tend
to
to form in gas clouds and they form in groups. And then they gradually depart. These open clusters gradually evaporate. And we can see several stars that share a lot of our motion around the galaxy. So if you take the stars in the Big Dipper and take the two stars that are at each end off, then those stars share our motion through space. So does Sirius and so does Procyon. So it's called the Ursa Major Moving Association. And it seems to be that we were part of a cluster that they were part of also.
Wow. And they can track the way they're going. They can make arrows go different directions.
Yeah.
We can see in the future, it's not gonna look anything like it looks like now at all. They're gonna be everywhere, aren't they?
Well,
Yeah.
the Big Dipper won't look like it either. It'll be
Okay.
all straight.
Are we touching a nerve, granddaughter? Gio? I think she's being hooked. She's still in the teen shy phase a little bit.
way to embarrass her, Grandpa.
Yeah.
This is the morning sky,
Uh-huh.
or excuse me, the evening sky.
Mars,
There's Mars. Somewhere is Venus.
right there. It's showing blue-green, so you were right by it a minute ago. It's just below Mars and Regulus. Right,
Oh,
right
there it is.
yeah.
Right next to the word Venus. I get it. And here's Mercury.
Ah.
Last week we showed Mercury in conjunction with the sun, and now this is July 11. This is tomorrow morning at 8 or tomorrow evening at 8 o'clock. So Mercury has moved to being an evening object here. And these are the constellations that are just setting. So say goodbye to them, Leo, and the galaxies looking out of the north pole of our galaxy. And this is a galaxy-rich region that is we'll say goodbye to until next winter, February and March. And
Okay,
then this sky is the morning sky,
So Uranus.
6 a.m. in the morning.
Uranus is at magnitude 5.8, barely seeable, or can we, what is
Yeah.
the limit of seeing 5?
Around 6, so you need a really good sky.
Yeah.
Okay.
Mhm.
That was my limiting magnitude last night out there at Gaviota was 6,
Wow, that was a good night.
Yeah.
Good sky.
but wiggly.
Yeah,
Do your telescopes tell you magnitude of things you're looking at?
no,
It doesn't. You just have to estimate it.
Well, no,
Well,
there's a meter that you can use it's like photographers use. So
Right.
you point at the sky and press a button and it gives you the luminosity per square arc second of the sky.
Okay. But what happened to Jupiter and what else is missing?
Saturn.
You're Oh yeah, Saturn, and then Neptune is too far out, I guess, right? And we never can see Pluto.
Yeah.
Okay.
But this is just pointing out that Uranus is quite bright.
And it's also blue.
Aha.
yes.
Well, I'm looking forward to talking about those little particles that go right through us at some point.
Next.
Here we go, friends. Methods of observing our universe. I see 8 items on there.
Yeah, we had, of course, visible light.
7 items.
Astronomy started out, and then we moved into the infrared and then radio waves after World War II. Ultraviolet light, we moved into that. We've been observing things now. We make satellites that go up and look in X-rays. And we've got, that should be waves, not eaves. Gravitational waves, we've come across that in the last few years. And now the most
Neutrinos.
elusive particles in the world and in the universe, neutrinos.
So they call this multi-messenger astronomy now.
Oh, do they?
Yeah.
Okay.
And they call them neutrinos because they're neutral. They're not polarized or
They're not charged.
And
okay.
Eno, because they're very small.
Yes.
But they're not a photon. They got some mass to them, right?
Yes.
At first they thought they were massless. And there's
Like
two
photons.
types of two ranges of neutrinos. The one that we're talking about here are high energy neutrinos. There are low energy neutrinos that come from the sun and from the core of stars. They're part of the fusion reaction. And we had theories about how many, because we model those reactions very well. And the theories predicted 3 times more neutrinos coming out of the sun than we were observing. And that was where they finally realized that there were 3 types of neutrinos, and neutrinos stay in one state for a certain period of time, and then they rotate into another type of neutrino. And so it takes a certain time. And by the time the neutrinos were all emitted from the sun, 2/3 of them or 2/3 of those neutrinos had become other types of neutrinos that weren't detectable at the time. So that was why it dropped down to 1/3 of its thing.
So there's always neutrinos in the solar wind.
There are neutrinos. They're not in the wind. They're independent of the wind. They have their own method of travel. The 3 types of neutrinos are electron neutrino, muon neutrino, and tau neutrino. And one of them may be massless. The other 2 have very small masses.
Okay.
I know this stuff is confusing. It's not well understood. It's hard to remember because it's so counterintuitive, at least for me.
And they rotate through those 3 types. So
Yes.
it's almost like they're gaining and losing mass, but it's not really.
But here we
Now-
are in Antarctica.
About 15, 20 years ago, the Gran Sasso labs in Italy thought that they had measured neutrinos traveling faster than the speed of light. And
Oh,
so there was a famous joke then about this neutrino walking into a bar and said, "Why is it so dark in here?"
Or the other end, you have the bartender goes, there was one from the other way, like the bartender says, we don't allow neutrinos in here, and a neutrino walks into the bar. But that was
Actually, the line is, so you became an ion, is that right? He said, yeah, I'm positive.
Yeah, right.
Okay.
An anion.
Another
So anyway,
part.
this is the surface of the facility on the surface. What they've done is melt through the ice. This is the ice top up here. They've melted through the ice with, I believe it was boiling water. And they've made a kilometer wide array of photosensors. They've buried them in the ice. And it's called the ice cube detector, of course.
Right.
So when and it's tricky to get data out of it because neutrinos pass through, they have almost no capture cross-section for matter. So they travel through the Earth. And these are different views of the globe. Antarctica is here. That's where the ice cube detector is. But stuff passes through the Earth from here. The Antarctica is down here, slightly on the other side of the globe.
That's actually Australia in that one.
Yeah, this one here is, but I mean, see, there's a radiant point right there next to it, and that's around the other side of the globe there.
Okay.
And so these are neutrinos headed for the detector and how they approach the Earth. And there's a slight, excuse me, I got to close the door here. The dog's going for a walk and she gets real excited.
He's going to tell us why it's got to be on the South Pole. Why couldn't that be anywhere? And why does it have to be underground or under ice? Why not on the surface?
It could be, no, it has to be a three-dimensional object, roughly cubic. It's a cube. And ice is the easiest thing to bury these in. And you will get, you could do it in granite. It doesn't matter. But it's really tough to put them down there. So it's easier just to bury them in the Antarctica. And so this is like trying to find out if there's an extra chamber in the Great Pyramid by looking at cosmic rays. It's a very subtle effect. The thickness of the Earth does attenuate slightly the neutrino flux heading for the South Pole. So you're in a sense, your detector is on the shade side, the neutrino shade side of the Earth. And as the Earth rotates, you'll get these varying signals from space depending on where the space is relative to the rotating Earth. It's a very subtle effect, and a lot of data reduction techniques were used to build up the paradigm to do the computer modeling. And
well, you mentioned the word cosmic rays, and I was going to ask you about that. What are they? Are they neutrinos?
yes,
No.
these
Well,
are
there are other things in cosmic rays, like protons and helium nuclei.
yeah, these are high energy component. This is a schematic that represents the aid of a satellite to identify a likely source of the high energy neutrinos. And it is NASA's Fermi satellite up here helped identify that source of neutrinos. It's not a neutrino detector, but the neutrino detectors are down here in the ice cube, and they can give a general direction of it, but then it's coordinated in this case with the Fermi detector and identified a monster black hole in a galaxy as the source of the high energy neutrinos seen by the ice cube.
Well, can I submit my stupid question of the week?
Go
Believe it
ahead.
or not, this occurs to me. We can't see them. They rarely hit anything, and they're out there and they have a little mass. Would it be possible to consider that it might be a form of dark matter? That maybe all dark matter is nothing but masses of neutrinos, which we're not going to see, and they're not going to hit most of us.
That's been looked at. That's not the source. This is a picture of our galaxy with the blue is superimposed on a photo of our galaxy. The blue is the neutrino sources, is the neutrino map from this thing. There's the large and small Magellanic Clouds. So, and this is the picture of our galaxy that was used, and this is the reduced results of neutrinos from the ice cube.
Ice cube.
Now, what is a neutrino?
Aha.
So, you got me. They travel they're nearly massless. They used to be believed to be have mass. They travel close to the speed of light, but slower, not faster. Reacts only to gravity and the weak nuclear force. Mostly passes through matter. It oscillates between flavors. Different types of neutrinos are called different flavors. Electron, muon, and tau, which I showed you a little earlier.
Okay.
It has a antimatter equivalent. That is, there are antineutrinos with these flavors.
Would the electron flavor be negatively charged, not neutral?
No, they're not charged.
They're not charged, and yet one's called
Yeah.
an electron neutron. Okay.
And nuclear processes produce neutrinos. The solar neutrinos are produced by the fusion in stars. So right now, billions of neutrinos pass through your body every second. So that itch you have on your shoulder, it's not neutrinos.
Whereas photons, which are massless, stop the minute they hit some solid, right?
If they are absorbed, if they produce a photon, they hit a nucleus or somehow interact with, I'm not raising my hand, it's just scratching, or interact
Ron,
with an
for
electron in
example-
an atom, they emit a photon.
Yes,
Yeah,
Chuck?
radio and X-ray photons pass right through you because they're not interacting with, things on your scale. So
So things in the color band or ultraviolet or infrared, they will stop.
maybe
immediately.
it depends. It depends on the size of the object they're interacting with.
All depends on the wavelength of the photon versus the size of the object.
But there's nothing in common between photons and neutrinos. They're two totally different animals.
No,
Yes.
everything, there is a relationship in that every particle in our universe also has a wave function associated with it, and vice versa. Every wave has a particle with it. So photons have a particle and a wave, neutrinos have a particle and a wave, but they're different. You have to intersect, you have to collect a neutrino to produce a photon. It carries energy, and it carries away 2 to 3% of our sun's energy.
But are they stored away in plasma inside the atoms that are being fused, and they suddenly let them go, just like a photon comes out of them?
Sometimes different nuclear reactions, different elementary particle reactions produce a neutrino.
Okay. And they're coming at us from all sides and directions, and yet they mostly go through everything.
Yeah.
Yep.
And would keep going forever, like
Until
photons
they hit something.
until they hit something. Okay. Wow. We're going to have to do a shot about matter and energy, the old E equals MC squared sometime, to clarify things. It just drives me nuts trying to get my mind around it. The minute something solid, which is mass, takes off, as you said early in the hour, Jerry, that's when, heat is the same thing as movement. But does the mass lose something? Does it lose a little bit of its weight and its mass by going somewhere and becoming, when you do energy, you burn a fireplace and the log's half gone.
Yes, the log, that's release of chemical energy. You change the chemical state of it because with heat, you oxidize molecules in the log, and they produce carbon dioxide as a gas, as a byproduct. But when they do, when the oxygen reaction occurs with a molecule of wood, in the product, an electron drops to a lower energy level, and that emits a photon, and that's what the flame is due to.
And then the rest turns into ash and smoke.
Yeah.
But something that's interesting to me is all those photons that are cruising across the universe, and we can see back, with the James Webb, 13 billion light years. That seems like a free trip to me, like free energy, but it isn't, is it? It's just not interfered with. It doesn't have friction. Like when we go on a trip, we don't get a boost and then get to drive there without any energy being expended. We got to fight the friction of the atmosphere. Photons don't have to do that, do they? Once they get kicked off, or neutrinos for that matter.
Okay, let's see. When you made a point earlier that you wanted to understand neutrinos or something else. Some things we don't know how to explain. And that's what's interesting about science. The other thing is that when we do explain it, even to ourselves, it's counterintuitive. So it takes some getting used to. It's not what you run across in everyday experience in quantum mechanics.
And in effect, Ron, those photons that you see from 13.8 billion years ago, they have lost some energy because space has expanded and stretched them out. So in some sense, they're, expending some effort to get here.
Huh.
Also,
Okay.
space photons interact with matter without being absorbed. When light hits a refractor's lens on a telescope, as light enters the lens, it runs into layers of atoms and it gets absorbed and instantly almost re-emitted layer by layer as it goes through the material. So that makes the effective speed of light in a material slower than in vacuum or air. So that ratio, we call that an index of refraction. And that's what causes light to bend when it goes into a lens.
But it never loses its speed. It just loses its frequency. That's
It
why we
slows
get
down. It actually slows down, Ron.
Yeah.
less than the speed of light.
Well,
It's the speed of light in a medium. So
Yeah.
the speed limit is the speed of light in a vacuum, but it has different speeds if it's passing through different substances.
Mhm.
Wow. Well, we're down to the end of the show, but boy, you got me tweaked there. Appreciate it. We'll talk about it more in the future, I guess. Did we cover everything, or is there something we're going to?
No, we covered everything.
We did.
That was perfectly timed.
Hot
Yeah.
Cameroon. That's the German word for twilight. Well, thank you for a great Saturday night and a great Friday night. And what's next before we go, Chuck? What's the new outreach?
Wednesday, we're at Carpinteria State Beach. Thursday, we're at Bacara. Friday, we're at Refugio State Beach. And Saturday, we're at Kachuma Lake.
And Bruce, you'll let us know what the Theater Organ Society is doing, mostly with the Arlington, right?
Yeah, I'll be the second person to know. You'll be the third person to know.
All right, guys. Thank your lovely wives, Pat, and what's your wife's name, Bonnie?
Bonnie.
All right, and we'll talk again for program number 126, I do believe, next Monday morning at 11 a.m. Appreciate it, everybody.